So this test lesson will be on hypothesis testing for variance and standard deviation. So one of the things we got to remember with variance and standard deviation is the symbols. So remember, variance, we use sigma squared for the population, and we use S squared for the sample data. And then standard deviation is sigma, and S is for the data when you're just have a sample size. So we have that information going on here. So again, remember when we do variance and standard deviation, we kind of did a confidence interval back in chapter 6. So hypothesis testing will kind of run along the same lines. We're going to use this chi-squared test. So chi-squared, we kind of have a symbol that looks like an X, but it's not an X. It's kind of a squiggly little guy. But, sounds like pi, but it's called chi-squared. So it has like a Ki sound to it, chi. So we're going to be using the chi-squared test. So remember, critical values come from the table. So remember, we had to find z-scores for normal distribution, and then the t-scores we had to use when we didn't know the standard deviation. And then the critical values here are going to be for variance and standard deviation and hypothesis testing is going to be this chi-squared. Now, the TI-84 really is not great for this test. So really, we're going to have to do more of a table setup on this. I think you recall we did a lot of that. We just used the calculator for calculations, but there weren't any of those shortcuts. So we actually have to stick with some of the formulas here in the problem. So again, when finding the critical values, again, this is going to be the table. This is where we'll be using the table. We need to know that level of significance. So we need to know what alpha is. So remember, level of significance is that alpha. We need to identify the degrees of freedom, which is going to be that n-1. Now, the catch is when we use the table, we have to pay attention to whether it's going to be right-tailed, left-tailed, or two-tailed. So remember, right-tailed, we're talking about greater than, left-tailed is going to be less than, and two-tailed is when that does not equal to. So notice how the right tail, we just use alpha. But to use the table, the left tail, we actually have to use 1 minus alpha. And then the two-tailed, we actually got to take half of alpha. That's going to give us our right chi-squared test. And then we have to use 1 minus half of alpha to get the left-tailed piece of this. So we also need to know the degrees of freedom here. So notice that when we look at these charts over here, 0 is actually over here on the left side. So unlike T and Z, we were dealing with the mean. And when we deal with the mean there, we were kind of doing, and also the population's proportion, the zeros out there in the middle. So we had like positive values and negative values. When we do the chi-squared test, all the critical values are going to be positive. So everything's going to be right at 0. So things have a little bit of a different look as we do this. So keep that in mind. 0 is over here on the far left. So all of our critical values are going to be positive as we move forward. So let's find the critical value of a right-tailed test. So to find a right-tailed test, based on our strategy, we just need to know the degrees of freedom and what alpha is. So do you remember to find the degrees of freedom, it's going to be the sample size minus 1. So we have n-1, which is going to give us this 26 minus 1, which is going to be 25. So right-tailed test, our graph is going to take on this look right here. And so remember, when we get into hypothesis testing, this is going to be what's called our rejected region. It's going to be right of chi-squared, this critical value. So to find the critical value, we have to use a table. So let me pause a moment and see if I can pull up a table for us here. So if we go to Blackboard, we have these PowerPoints as well. I'll do this one from the PowerPoint. So in the Unit 4 PowerPoints, we have hypothesis testing for variance and standard deviation. Let's see if we can get this to open. And so we kind of see the table is actually going to be the last slide on this thing. So if I scroll all the way down to the last slide, this is going to be our chi-square distribution here. See if I make that a little bit bigger. That's not too bad. Okay, so we can kind of see our degrees of freedom and our alphas across the top here. So we got that kind of pulled up here. All right, let's see if I can. So if we want to find the critical value, we have to use our table. So our degrees of freedom was to 25 and alpha was 0.10. So if I go back to our table, so 0.10, stay on that, and then we said 25. So we have this 34.382. 34.382. So our chi-squared is going to be then 3. I lost my mind there. So it's 3.482. I done forgot. I was trying to play with my pencil here and lost myself. So 0.10 and 25. So 34.382. Is that what I said? I don't know if I see what I said. Let's see here. Yeah, 0.10 and 25. 0.10 and 25. So 34.382. So not bad. Just lost that one number there. So 34.382. So sometimes they'll ask us to round to 2 places. Sometimes they'll round to 3. So watch that in Blackboard. So that's where I almost like to have a hard copy of this in front of me so I don't have to go back and forth on this here. Let's see here. Stuff organized here. So it could be 34.32 or 34.38. Since this 2, we just say round down to the 34.38. So it's going to be our critical value. So if we're right of that, this would be our rejection region. So if we're greater than this 34.38, that's going to be in our rejection region. So remember, 0 is over here. So if I have to look at this with respect to the 34.38, make sure we compare it very closely there. So finding the critical value of a left-tailed test. So left-tailed, notice how we actually have to use 1 minus alpha to get our value there in our table. So we have to go 1 minus 0.01, which is going to be 0.99. Again, you can just calculate if you need to for that. So degrees of freedom is going to be the 11 minus 1 would be 10. So if you use that information there, I can find the critical value for a left-tailed test. So 0.99 and 0.10, or 0.99, and then degrees of freedom is 10. So 0.99 degrees for freedom of 10 is 2.558. 2.558. So chi squared is going to equal this 2.558. Double check myself there. Yeah, 2.558. So again, if I am rounding to 2 decimal places, that would be 2.56 because it's 8, which say the 5 would round on up to a 6. So pay attention in your homework because sometimes they'll ask you around for 2 places, sometimes they'll ask for 3. So most commonly it'll be 3, so it's not that big a deal, but every once in a while they'll throw one in there where they'll ask you to round to 2. So lastly, we have a two-tailed test. So we now have chi squared left, chi squared right. So notice that chi squared left is going to be the closest one to 0. Chi squared right is going to be the furthest one away from 0. So we have that kind of going on there. So if I want to find chi squared right, that's just going to be half of alpha. So if alpha is 0.05, we got to divide that by 2 to get using the table there. So that's going to be 0.025. And then chi squared L is going to be the left one. That's going to actually be 1 minus 1/2 alpha. Or in other words, that's just going to be 1 minus 0.025. And that's going to be 0.975. So if we use a calculator, we can get that as well. So if it's two-tailed, we have to find 2 rejection regions. So for the first one, we have this 0.025, and notice that the degrees of freedom on these is going to be 9 minus 1 would be 8. So we have this 0.025 and this 8. So 0.025 and 8, that's going to be 17.535. So 17.535. So that would be our chi squared R. So if I want to do chi squared L, you got to use this 0.975 with the degrees of freedom of 8. So 0.975 with the degrees of freedom of 8. So 0.9758. So we're seeing this 2.180 as our value, 2.180. So on this one, notice that you would have to be greater than 17.535. That would be where you have to be in the rejection region. And over here, you'd have to be less than 2. Put that in a little bit different spot there, so I'm not all over the place there. So you could say, I probably could have just did them down here. So less than 2.180 would be this rejection region here. So, and then your rejection region over here would be greater than 17.535. So we got to pay attention to our inequalities there. So again, in this one, you're going to have like you're going to have to find your test statistic as well. So that's probably what we're going to be moving into now, is finding what the test statistic is. So to actually perform the chi-square test, one of the things is we have to know that this is normally distributed. So normal distribution has to be in play here, but notice how there's not a second option. Before we had this sample size being greater than or equal to 30, or NQ had to be greater than or equal to 5, and NP had to be greater than or equal to 5. We don't have those choices here. So for chi-squared test for standard deviation or variance, the only thing we have to go on is normal distribution. There's no sample size being greater than or equal to 30 here. So again, variance is this sigma squared and standard deviation is sigma. So we have to pay attention to that as well. So to find our test statistic, we have this formula here to find our test statistic. So this is going to tell us where we are with respect to the critical values. So we have to use this formula here, where remember n-1 is the degrees of freedom, s squared is the variance of the sample, and sigma squared is the hypothesis variance, if you will, or the population. So again, we still are talking about the degrees of freedom being n-1 here. So that's kind of what we're doing. So notice how we just have this one formula, and our one formula involves variance. So if we're given the standard deviation, we're going to have to square it to get to the variance. So pay attention to that as we do this formula, that if they give us standard deviation, we have to square that to get variance. So it's really important to pay attention to that wording in the problems. So again, to perform this chi-square test, so this is hypothesis testing for standard deviation or variance. So the first thing is they have to mention something about being normally distributed. So if that's not true, then we have to we can't use this testing. So again, like before, we're stating our null hypothesis and our alternative hypothesis. So remember, the null hypothesis is always some type of equality. So greater than or equal to, less than or equal to, or equal to, where the alternative hypothesis is always going to be the greater than, the less than, or the not equal to. And remember, these will tell you whether it's left-tailed, right-tailed, so forth. So notice that greater than means you're going to be right-tailed. Less than is going to be left-tailed. And not equal to is going to refer to a two-tailed. So remember, for level of significance, here we would have alpha. Here we'd have to have 1 minus alpha. And two-tailed, remember there's two situations. One half alpha is one of them. And then 1 minus 1/2 alpha is what we use to get the other critical value. So that's where we have to also know the degrees of freedom. And we're going to use the table. Actually, we're going to use the PowerPoint table this time. And we have to use this formula to actually do the test statistic. Again, n-1 represents the degrees of freedom. S squared represents the variance of the sample. And sigma squared represents the variance of the hypothesis, or the population, if you will. So we have to make a decision to reject or to fail to reject the null hypothesis. So if chi-squared is in the rejection region, then we reject the null hypothesis. Otherwise, we fail to reject the null hypothesis. And then we have to make this interpretation from the information. So let's look at an example here. As we move into this example, we also want to there's a video that you can watch as well in your video lessons about how to interpret a hypothesis. That very last sentence, that gets kind of confusing on the wording. So one thing is, we'll talk about this as I get further into this example here and see if we can put this all together. So the first example here, again, is going to be using a hypothesis test for a population variance. So a dairy processing company claims that the variance of the amount of fat in whole milk processed by the company is no more than 0.25. So no more means you can be 0.25, but you have to be less than that as well. So that's a less than or equal to symbol. So that's the claim as well. So pick up on that. That's our claim. you suspect this is wrong and find that a random sample of 41 milk containers has a variance of 0.27 at a level of significance of 0.05. Is there enough information to reject the company's claim? Assume the population is normally distributed. So that's important for them to say that. So now we can move on. So the first thing is your hypothesis. So what is your null hypothesis and what is your alternative hypothesis? So notice how the less than equal to is the claim. That's going to be part of the null hypothesis. And since today we're talking about variance, variance is going to be sigma squared. So sigma squared is going to be greater than or equal to, I'm sorry, less than or equal to, because it says no more than. So we have to be less than or equal to this 0.25. That's the claim. And then the alternate hypothesis is the opposite of that, or the complement. So sigma squared would be greater than 0.25. So the next thing we need is, lost something there. That all looks okay. Okay. I don't know where that came from. So the next thing we need to do is get our critical value. So the critical value is from the table. So to use the table, we got to pick up on whether this is left-tailed, right-tailed, or two-tailed. That comes from the alternative hypothesis. So notice how it's greater than. Greater than means we're talking about a right-tailed curve. So we're looking at this guy right here. Get that over here. So the critical value from our table, since it's right-tailed, we just need to know what alpha is. So alpha is that level of significance. And that was given as 0.05 in our information. And we need to know the degrees of freedom. So the degrees of freedom, remember, that's the sample size minus 1. So they did a random sample of 41 milk containers. So our degrees of freedom is going to be 40. So if you use that information there, we can now determine what the critical value is. So if we go to our table, we need 0.05 and 40. So 0.05 and 40. So we end up with this 55.758. So we have 55.758. So that's what chi-squared is as far as our critical value goes. It's going to be chi-squared 0, if you will, our critical value. So again, if we round it to 2 decimal places, that's going to be 55.76. So notice that to reject this, what's got to happen here is we got to be greater than that. So if chi-squared is going to be greater than 55.76, then we will be rejecting the null hypothesis. If it's not greater than that, then we would be failing to reject it. So the next thing is to find that that test statistic. So the test statistic. So what we use here is the formula. So to find the test statistic, chi-squared, we have the degrees of freedom, which is n-1, times the variance sample divided by the variance that was given to us from the hypothesis. So our degrees of freedom, like I said, we had 41 milk cows, so that's going to be a 40. Then we're going to multiply it by the variance from the sample. So that has a variance of 0.27. That's mentioned right there, the variance of 0.27. So 0.27 is our variance. And then we have to divide it by what the hypothesis variance was. So they said no more than 0.25. That's our hypothesis variance. So we have 0.25 here. So if we do that math, that'll give us our test statistic, and we're going to compare that to the critical value. So let me slide this over a little bit. So let's see here. Let's get that back down. So we're going to multiply. Again, you can use the alpha button if you want there, since we already got it set up nicely. 40 times 0.27, then divided by 0.25. That gives us then this 43.2. 43.2. So our test statistic is 43.2. So looking at our graph, so here's 0 over here. Does 43.2 go out past 55.76? I would actually fall short. So 43.32 is going to fall in the non-rejection region. So this is going to tell us to fail to reject. So this says fail to reject the, get my spelling down better. So we're going to fail to reject the null hypothesis. So then it comes to our interpretation. What's our conclusion? So our conclusion is where, let me make this a little bit bigger now. So one thing we pick up in our table here is when it comes to the claim, we're going to use reject, or so notice how reject goes with the claim. The alternative hypothesis, notice how the word support shows up each time. So it depends on where our claim is. And also, if our claim is the null hypothesis, we're going to be using these words reject. If our claim is the alternative hypothesis, we're going to be using these words like support. So based on what we said here to begin with, we said our claim was the null hypothesis. Since we said our claim was the null hypothesis, our vocabulary needs to be using this word reject. So since we failed to reject the null hypothesis, that means we're keeping the null hypothesis. So that means there is not enough information to reject the claim. As we're not rejecting the claim. So we need to be seeing this word reject in there, not the word support. So keep that in mind when you make your interpretation. There is not enough information to reject the claim, because our claim was less than 0.25, so we're not throwing that out. So we're not rejecting the claim. So see if that helps a little bit. So if your claim is, again, the null hypothesis, in your phrasing, you should have this word reject in it. If you have the alternative hypothesis as your claim, there should be the word support associated with your interpretation. So, and just go double check again up here. Notice how here we failed to reject. Just notice how it says there is not enough information to reject the claim. That's kind of what we came up with. So we kind of put that down. So it's not a bad idea to put this down somewhere in your notes to kind of help you keep straight on that final statement, because that's what kind of spun me around, is using the correct wording they want there.
I do this.
So our next example is use a hypothesis test for a standard deviation. So remember, standard deviation is going to be sigma.
Mm-hmm.
So company claims that the standard deviation of lengths of time it takes an incoming telephone call to be transferred to the correct office is less than 1.4 minutes. So there's our claim right there, less than 1.4 minutes. A random sample of 25 incoming telephone calls has a standard deviation of 1.1 minutes. At a level of significance of 0.10, in other words, a 10%, is there enough evidence to support the company's claim? Again, assume that the company's population is normally distributed. So since they say that, our first step is, again, the hypothesis. So we always have to have this null hypothesis and the alternative hypothesis. So now notice how we're talking about the standard deviation. Notice how it says less than 1.4 minutes. That has to fall under the alternative hypothesis. So S has got to be, sigma has got to be less than 1.4 minutes, which means our null hypothesis is going to be the other side of that. So sigma is going to be greater than or equal to 1.4 minutes. And notice how this is our claim down here. So it's important to pick up on where the claim is. So our next step is to identify the critical values. This is going to be the table. To do the table, we have to understand whether it's left-tailed or right-tailed. So notice that our alternative hypothesis is less than. Less than means we have a left tail. So when it comes to a graph, bear with me here, pull this down, one of those left-tailed guys up here. So the left-tailed test should look something like this here. Let's see if we can find a home for this somewhere. Okay. So the rejection region is going to be, has to be less than this, our critical value that we're looking for. So we're looking for chi-squared 0, which is denoted as our critical value. So that's where our table comes from. So again, we need to know, in this case, 1 minus alpha. So for the left tail, you have to actually do 1 minus alpha. So since we had a 0.10, we're going to have 1 minus 0.10, which is going to be 0.90. So we got to pick up on that we actually have to use 1 minus alpha this time. And then our degrees of freedom, since there's 25 in our sample, degrees of freedom would be then this 24. So I'm using this 0.90 and this 24 to identify our critical value. So 0.90 and 24. Let's make this a little bit bigger. 0.90 and 24. So I'm coming up with this 15.659. 15.659. So that's going to be our chi-squared 0. That's going to equal this 15.659. That's if it's 3 decimal places. If it's 2 decimal places, you would say 15.66 if you're writing to 2 decimal places. So you just have to pay attention to how they want that in my lab on that. So once we have that, our next step then is to find the test statistic. So we're going to test this against our critical value. So to do that, to find this chi-squared test statistic, we have to use n-1, which is the degrees of freedom, times the variance of the sample divided by the hypothesis variance. So notice how they gave us standard deviation. So to do they said S was 1.1. Notice how it says 25 incoming telephone calls. That's a standard deviation of 1.1. So S is going to be 1.1. So S squared is going to be 1.1 squared. And the standard deviation for the hypothesis, they said, was this 1.4. So that was our sigma, was 1.4. So we actually have to have the variance to use our formula. So we have to use this 1.4 squared to do this problem. So to find chi squared, our degrees of freedom, this is a 25, our degrees of freedom was this 24. We have to have a 1.1 squared here and a 1.4 squared here for our variances. So we can't substitute those standard deviations straight in the formula because our formula involves variances. So if I can slide this over. So I use my alpha button, alpha F1. So I have 24 times 1.1 squared. Then on the bottom, I have 1.4 squared. Hit enter, and I get 14.816. Or 14.82. So the next thing is compare that to the 15.69. So if I put that in there, is 14.82, is that less than 16.859? Yeah, so that means it is in the critical region. So that would actually fall over here somewhere. So since 14.82 is less than 15.66, if you will, we could say then we're going to be rejecting, because it falls in the rejection region. So we're going to be rejecting the null hypothesis. So again, in our conclusion, though, what was our claim? Was our claim, let's see, our claim was actually the alternative hypothesis. So we should be using this word support. So if I can make this a little bit bigger, since we did reject the null hypothesis and our claim was the alternative hypothesis, notice how there is not enough information, there's not enough evidence to support the claim. So we'd end up with that as our phrase. I'm sorry, we rejected it, didn't we? So if rejected, there is enough information to support the claim. That makes better sense. I was like, what? So since we rejected the null hypothesis, we're in this first row up here. We rejected the null hypothesis. And since our claim was alternative hypothesis, we should have enough information then to support the claim. That's kind of our conclusion. So since we rejected the null, it makes sense to like the alternative. So there is enough information to support the claim. So again, one of the keys to pick up on to start with is rejection has everything to do with the word reject is going to have everything to do with the null hypothesis, and the word support is going to have everything to do with the alternative hypothesis. So example 6, using the hypothesis test for a population variance. So if we look at this one here, a sporting goods manufacturer claims that the variance of the strengths of a certain fishing line is 15.9. Notice how it says is 15.59. So that means we have an equal sign here. A random sample of 15 fishing line spools has a variance of 20.18. At a level of significance of 0.05, is there enough evidence to reject the manufacturer's claim? So assume the population is normally distributed. So again, our first step is the hypotheses. So the null hypothesis and the alternative hypothesis. So equals 15.59, that's going to have to go with this here. And also we're talking about variance. So this is sigma squared. So sigma squared is going to equal this 15.59. And the complement of that would be sigma squared does not equal 15.59. So this is our claim, though. Our claim is that it is 15.9. So whatever that strength means to them. So from there, to kind of reject or fail to reject, we have to understand what our critical value is. So the critical value has to come from the table. So remember, since this is not equal to, this means we have a two-tailed. So I'll come up here and pull that down. So two-tailed means we're looking at this here. Let's move that over here out of the way. But that's kind of what our graph is going to look like, is that. So to find the critical value, we need to know what half alpha is to start with. So since alpha was 0.05, the first thing we have to pick up on is what is half alpha. That's going to be 0.05 divided by 2, which is going to be 0.025. And then we also need to know 1 minus half alpha. In other words, what is 1 minus 0.025? So that should be 0.025. And that should be then 1 minus 0.025 would be 0.975. So we got those, we got our new alphas, and then we have to also know our degrees of freedom. So since the sample size was 15, we have a 15 up here. We know that our degrees of freedom is going to be then this 14. So again, we have to find chi-squared R and L. So chi-squared R and chi-squared L. So remember, chi-squared R is the one that's going to be furthest to the right. So it's going to be the bigger value. So 0.025 and the 14. So 0.025 and the 14. That gives us this 26.119. So that's going to be this guy out here. So 26.119. That's going to be our critical value over here. So we're going to have to be greater than 26.119 to be in the rejected region. And then chi-squared L, we're going to use 0.975 with the 14. 0.975 with the 14. So I'm seeing 5.629. 5.629. So that means over here, we're getting this 5.629. And notice that our critical value has to be less than that. So we got to be left of that. So here, basically, what we're saying is chi-squared L, if we are, let me try that again. So when we get our test statistic, chi-squared, if it's less than 5.625, we're going to be rejecting. If chi-squared is greater than 26.119, we also reject. So if we're right of the 26.119, and if we're left of 5.625, we reject. Because remember, 0 is over here on the far left. So our next thing is we have to find our test statistics here, our t. So we need to find chi-squared and see where it is. So to find chi-squared, we need to know the degrees of freedom. And on the top, we have to have the sample variance divided by the hypothesis variance, if you will. So our degrees of freedom was this 14. The variance was given to us. These were variances up here. So 15.9 was the variance. I'm sorry, that's the bottom though. That's the population variance. The sample variance they found was 21.8. So the 21.8 is the variance. So we don't have to change those there. That's what S squared actually stands for, is the variance. So if I use my calculator, we put that in. I'll have to slide this over again. So alpha F1, we have 14 times 21.8. And on the bottom, we have 15.9. And if we enter, we get this 19.195. Notice we can't round to 3 places. We have to go out to the 4, but that 9 means change it to a 5. So if we're going out to 3 decimal places, this is going to be 19.195. So the question is 19.195 less than 5.65? No. Is 19.195 greater than 26.19119? So let me pull that up there a little bit bigger. So if you compare this number here, it's not less than 5.625, so it's not in the left critical region, left rejection region, and it's not greater than 26.199. So it falls in what's called the failed reject region. It's in kind of the safe zone. So this would say fail to reject the null hypothesis. Fail to reject the null hypothesis. So our conclusion then, it's based on where the claim is. So notice how our claim is the null hypothesis. So we're going to be using something with the word reject in it. So if we go back up here to the top, so we failed to reject it. So there is not enough evidence to reject the claim. So notice how we can't say support. We have to use the word reject. So since we failed to reject the null hypothesis, there's not enough evidence to reject the claim. We have to keep it. So that's kind of what we pick up here. This is that. Since we're not rejecting, there is not enough evidence to reject the claim. So again, if the claim is still with the null hypothesis, our phrasing has something to do with the word reject. If our claim was the alternative hypothesis, we would have to be using some type of verbiage that said support one way or the other. Okay. Let me do one more example if you want. If you think you've got enough here, you don't have to do this example, but if you want to see one more example, this comes from your homework as well. So we'll do one more here and see where this takes us. So quarters are currently minted with weights normally distributed and having a standard deviation of 0.062. So that's kind of an is thing. So we have that kind of going on there. So notice how they had a standard deviation is sigma. Now, new equipment is being tested in an attempt to improve quality by reducing variation. The simple random sample of 27 quarters is obtained from those manufactured with new equipment. And this sample has a standard deviation of 0.041. So again, they're using standard deviations here. Use 0.05 for level of significance, and also how that's going to be our alpha. To test the claim of quarters manufactured with new equipment have weights with a standard deviation less than 0.0625. So actually their claim is down here that they're looking for, not up here. So they kind of move the claim on us. So we want to be less than 0.062. So that's what we're looking for. So if it's less than 0.062, that's what they're claiming. So does the new equipment to be effective in reducing the variation? So if it's less than, then yeah. If it's not less than, then no. So again, our first thing is the null hypothesis and the alternative hypothesis. So again, there's talk about standard deviation. So the standard deviation is going to be less than this 0.062. That's given as our standard deviation there. And then the null hypothesis has got to be the flip of that, which means it's got to be greater than or equal to 0.062. But also, this is what they're claiming, is they're saying that there's a really good tight variance here. There's not much change at all. So that's a good thing. So that's what they're looking for, is very little variance, 0.062. If it's greater than that, then the new equipment is not doing its job. So the next thing we need to do is find the critical value. So the critical value, notice how since we have less than, we know this is left-tailed. And we know that the degrees of freedom is going to be, the sample is 27, so it's going to be a 26. Left-tailed means we have to actually use 1 minus alpha. So alpha was the 0.05, so we actually got to use 1 minus this 0.05. So our new alpha is going to actually be 0.975. I'm sorry, be point. I may have to actually subtract that one. My brain just went down. 1 minus 0.05. Yeah, 0.95. Okay. So I didn't look right. Yeah, so 100% minus 5%, 95%. There you go. Sometimes just got to do it. So that's going to give us our chi-squared 0, which is our critical value. So that comes from the table. So in the table, we need 0.95 and 26. So 0.95 and 26. So make that a little bigger. I can't really see that. 0.95 and 26. So that's going to be 15.379. 15.379. So 15.379. So that's going to be our critical value. So again, since we said this is left-tailed, we need a left model. This one here looks left-tailed. Let's see if I can find my little guy here. There we go. Lost it again. Where'd you go? Down here where I can see you. Okay. Come on, you can move. You can move. There you go. There you go. There we go. All right. So left-tailed. So that's how we have to be less than this critical value of 15.379 to be in the fill region. So let me double check myself there. 0.95, 26. 0.95, 26. So 15.379. Okay. So 15.379. Okay. So the next thing is we have to find our test statistic. We have to compare it to see if it actually falls in the reject region or not. So to find the test statistic, we have to have our degrees of freedom, which is the 26 times then. Notice how again, we had the sigma and S is what we had. So sigma is this 0.62, that's 0.062 is our standard deviation. So we have to do sigma squared, which is going to actually be 0.062 squared. And the standard deviation for the sample, they said was the sample has a standard deviation of 0.041 is what they had. So 0.041 was the, let's see here. So S squared is actually going to be 0.041 squared. So 26 times then 0.041 squared over the variance hypothesis would be hypothesis variance would be 0.062 squared. So if we put that into our calculator, clear that off. So again, we have a fraction. So we have the 26 times 0.041 squared, and then we have 0.062 squared. Hit enter, and we get our test statistic is going to be this 11 point. So we have 11.3699. So it's going to be actually 11.370. So 69, we have to round up to 70. It's 11.3699. So yeah, 11.370. So what we're trying to do now is compare that to the 15.379. Remember, our critical value was the 15.379. So the question is, if 0 is here, notice that the 11.370 is going to be less than 15.379. So it's going to fall in the rejection region. So what we'll pick up on then is we are going to reject the null hypothesis. It falls in the rejection region. So the question is, what was our claim? Notice our claim was actually the alternative. So if it's the alternative, we have to use this word support. So since we are rejecting the null hypothesis, there is enough evidence to support the claim. So again, if we go back up to that table, we reject the null hypothesis, but the claim is the alternative hypothesis. Notice how that fits this right here. There is enough information, there is enough evidence to support the claim. So we have that conclusion there. All righty. There is enough evidence to support the claim. So that takes us through chapter 7. Y'all have a good day.